Hi everyone. In Unit 3, we're going to learn how to graph rational functions. We're going to start with finding intercepts and horizontal asymptote and vertical asymptote of a rational function first. So today, this is what we're going to learn: intercepts, vertical and horizontal asymptotes. Let's first of all see what is a rational function. A rational function is any function which can be defined by a rational fraction, like for example 2 over x, or x squared minus 3 over 3x plus 5. So these are rational functions, but if I give you, for example, x plus 5 over 9, this is not a rational function because your variable is not in the denominator. This is just a simple linear function. Intercepts are the points at which a graph crosses either x or y axis. For example, if this is my graph, this point that my graph is crossing the x-axis is called x-intercept, and this one which is crossing the y-axis is called y-intercept. We'll talk more about intercepts later. Let's find the graph of a parent rational function here. First of all, the equation of a parent rational function looks like 1 over x. The graph of this function, we know that we have a vertical asymptote at x equal to 0 and a horizontal asymptote at y equal to 0. So these are our asymptotes: y equal to 0, and this one is x equal to 0. And the graph of your function is trying to get close to these asymptotes like this. So this line tries to get close to 0 and pass it, but this asymptote, the vertical asymptote, doesn't let the graph pass through this line. The same is here. This line, this graph is trying to pass y equal to 0, but the asymptote of y equal to 0 doesn't let him pass. The same is here. Your graph is trying to get close to your function and trying to pass, but the asymptotes don't let them. The definition of an asymptote is a line that your graph is trying to approach that line, gets close, but doesn't pass that line. Now let's find the domain of this function. For domain, we know that we are looking for x values. So we need to move from left to right because the left side values of the x-axis are the lower parts, and we start always from the lower numbers and go to the higher numbers. So this is left to right. As I move from left to right, because I know this function is continuing to the left side, that means my function is starting from the left side. So it starts from negative infinity, and then it's going to the right side. As I move to the right side, for any x value that I see on the x-axis, there is one point on the graph which is defined for that x value. But as I reach to the 0, I see that there is nothing defined for x equal to 0. Your function is not defined for x equal to 0. That means there is a hole here at this point. So as I move from left to right, I reach to 0. I have to make a jump and go after 0, and then again continue. As I go after 0, again everything is defined for my graph. So I move from negative infinity to 0, and then I stop and jump, go to the point after 0. So it's here, 0 to infinity. So this is my domain. Basically, if you want to find the domain of a rational function, you just need to exclude the asymptote. Exclude the vertical asymptote. So everything except the vertical asymptote, which here is x equal to 0. Then for range, we need to move bottom to top. We're looking for y values, and we know that on the y-axis, the bottom side are the lowest points and the top side are the highest points. So as I move from bottom to top, because my function is again continuing to decrease from this side, that means I'm starting from negative infinity. The same story is here. As I move up, for all the y values, there is some point on the graph. So that means all these y values are defined except the y equal to 0. At this point, there is no point on the graph that we can find. So we have to make a jump and go after this 0 and again continue moving. And after 0 again, all the y values are defined. So again, I'm going to write it like this: negative infinity to 0. Then I make a jump and add the 0 to infinity to my domain. Here, to find the range of rational function, exclude the horizontal asymptote. So you're gonna have everything defined except your horizontal asymptote, which here is y equal to 0. Now we want to find the end behaviors of functions. Let's first of all start with the parent function, which is this is 1 over x. So y equal to 1 over x is the equation of this parent rational function. So the end behaviors are this one, this one, this one, and this one. We have 4 end behavior, 4 ends actually on our function. So we need to decide what is happening to our x and y on each of these end behaviors. So let's start from here. As I move on my function, like as I'm moving here to this side, I see that x is going to decrease. It's going to left side and it's going to negative infinity. So x is going to negative infinity. And I want to know, as x is going to negative infinity, what is happening to my y? As you see, the y is trying to get close to 0 but doesn't pass because we have an asymptote here. This asymptote doesn't let the y pass the y equal to 0. So this means my y is getting close to 0. Now let's talk about this side. On this side, again, x is just continuing to move to the right side. It's going to infinity. So let's just make this clear. Okay, so here x goes to negative infinity, and on this side goes to negative infinity, and on this side x is going to positive infinity. Now what is y doing at this point? As you see, as you move on the graph, you see that the y value is getting closer and closer to 0, but this asymptote that we have here doesn't let your y actually pass through this point. So your y is just getting close to 0 and cannot pass it. Now let's talk about this end behavior over here. As you move on this point of this part of your graph, your x is getting close to 0. As you move here, just check your x values. They are getting closer and closer to 0, but they cannot pass 0 because we have an asymptote here. So on this side, x is getting close to 0. But because it's getting close to 0 from the left side, x is approaching 0 from the left side, we're going to put a small negative on top of this y to show that this is getting close to 0 from the left side. And then what is y doing here? Y is just decreasing forever. It's going down and down. So y is going to negative infinity. Now let's talk about this end behavior over here. As you see, we are moving on the graph. The x is getting close to 0 again, but from the right side. So we can say x is getting close to 0 from the right side. So we put a small positive sign here, plus sign here. And what is y doing? Y is just increasing, going up forever. So this is y going to infinity. The asymptotes that we had was were x equal to 0 and y equal to 0. These were the asymptotes that we had here. On the other function, the other graph that we see here, we can easily find a vertical asymptote here, which is at x equal to 1. So our vertical asymptote is at x equal to 1, and horizontal asymptote is here, and it's at y equal to 3. Notice that always vertical asymptote, because it's a vertical line, it's x equal to something, and horizontal asymptote is a horizontal line, and equation of a horizontal line always is y equal to something. Now let's talk about the end behaviors. For this end behavior over here, x is going to negative infinity because x is going to left and it's continuing. But your y is trying to get close to this line, which is y equal to 3, and cannot pass it because the asymptote doesn't let him go. So y is getting close to 3. On this side, again, same thing is happening. X is increasing and going to positive infinity, and y is trying to get close to this y equal to 0, but the y equal to 0 is the asymptote that doesn't let him pass. So y is getting close to 0. Now, what is happening to your x at this endpoint? At this end side of your function, x is trying to, because as you move on your graph, you see on this side, x is just getting close to 0. You'll just check your x values as you move on your function. The x values are getting less and less and less, and they're trying to get close to 1 actually. This is x equal to 1. They're trying to get close to 1, but this asymptote at x equal to 1 doesn't let them pass. So x is getting close to 1, but it's getting close from the left side, so we're going to put a negative sign here. Then what is happening to your y? Y is just decreasing, going down and down forever, so going to negative infinity. Now what is happening to your y value? X is trying to get close to 1 here again, but from the right side. Now I can see that the y value is increasing, it's going up forever, so it's going to positive infinity. So this is the end behavior of this function. Here we have the general form of transformation of a rational function. The general form is 1 over x plus h and plus k. This h is happening to x. Whatever is happening to x means it's moving horizontally either to left or to the right side. So I'm going to write this as horizontal shift. And this k is happening to the y value, so it's moving vertically up or down. So this is vertical shift. On this example that you see here, we have 1 over x plus 3. We know that the inside the function always behaves like kind of inverse. We have x plus 3, but your function is going to move left 3. And then you have minus 2, means your function is going to move down 2. In order to graph this function, we know that if we had the parent function, we would have a vertical asymptote at x equal to 0 and a horizontal asymptote at y equal to 0. So this is our asymptote at y equal to 0. But we are moving left 3 and down 2. So we're going to do the same thing on our asymptotes first. This asymptote is going to move left 3, 1, 2, 3 to the left. And if I move this down 2, we're not going to see anything because this is just a vertical straight line, and it's continuing forever. So if I move it down, I don't see anything. Actually, I don't see any change. So basically whatever I see is just left 3. But about the horizontal asymptote, if I move this asymptote left 3 again, we are not going to see anything because it's just moving left to right and it's just a horizontal line. But down 2 is something that I can easily see. It's moving down 2. So the first thing in order to graph a rational function is to find the asymptotes, how asymptotes are moved. Then all you need to do is to graph your function in a way that your graph is getting close to asymptote but doesn't pass. So it's going to be something like this. This is the graph of function. Again, your domain, we are going to write the domain by excluding the asymptotes. Like here, asymptote is x equal to negative 3. So we're going to write negative infinity to negative 3 and negative 3 to infinity. And the horizontal asymptote is y equal to negative 2. It was 0, but now because we moved down 2, it's at y equal to negative 2. So now the asymptote is, the range of this function is negative infinity to negative 2 and negative 2 to infinity. Okay. Now let's find intercepts of a rational function. To find the x-intercept, we know that, like, if this is my graph, y-intercept is here. At this point, x is equal to 0 because it's crossing y-axis. So in order to find the y-intercept, you just need to plug in 0 for x and solve for y. So here I'm going to plug x equal to 0 in our function. So for y-intercept, set x equal to 0 and try to solve for y. So this will be 2 times 0 plus 1. Wherever you see an x, you're going to plug 0 for that x. And this is 0 minus 1. 2 times 0 is just 0. 0 plus 1 is 1. 0 minus 1 is negative 1. And 1 over negative 1 is negative 1. So your y-intercept is 0 and negative 1. To find the x-intercept, all you need to do is to set the numerator or the top of your function equal to 0. Why is this happening? Because on your function, on your graph here, this is where you have x-intercept. At this point, y is equal to 0. Basically, if you want to find the x-intercept, you need to set the y equal to 0. But if you have a fraction, like a rational function, let's say, for example, I have 2x plus 1 over x minus 3. This is my y. So I want to set the y equal to 0 and then solve for x. Whenever you have a rational expression and that's equal to 0, this means only your top needs to be equal to 0. The bottom, you don't even need to touch that. Just ignore the bottom. Just set the top equal to 0. Because in a rational expression, when the rational expression is equal to 0, only top is equal to 0. We know that we cannot set the bottom equal to 0 because anything divided by 0 is undefined. So that's why we don't have to set the bottom equal to 0. Okay, so here I want to find the x-intercept. I just set the top equal to 0, which is 2x plus 1 equal to 0. And then I try to solve for x. Subtract 1, so this will be 2x equal to negative 1. Then you divide by 2. Then you will have x equal to negative 1 over 2. So your x-intercept is negative 1 over 2 and 0. Now let's find the x-intercept and y-intercept for this one. Y-intercept, you just set x equal to 0 and solve for y. So this is 0 plus 10 over 0 squared minus 25. So this will be 10 over negative 25, and we simplify, this will be 2 over negative 5. So your y-intercept is 0 and 2 over negative 5. Now what is my x-intercept? For x-intercept, you just set the top equal to 0. X plus 10 equal to 0. Then you solve for x. Subtract 10 from both sides. Then x will be negative 10. This is your x-intercept. Negative 10 and 0. The next function, again we want to find y-intercept first. X equal to 0. So you plug 0 into your function. It will be 0 squared minus 3 times 0 plus 2 over 0 squared minus 6 times 0 plus 9. So all these will be 0 because 0 times 3 is 0, 0 squared is also 0, so you only have 2 over 9. So your y-intercept is 0 and 2 over 9. What is x-intercept? You need to set the top equal to 0. X squared minus 3x plus 2 equal to 0. Now we want to solve this for x. The best way to solve this is to factor. So if I factor this, on top I use the big X way to factor the polynomial. On top goes a times c, which is 1 times 2 is 2. At the bottom goes the b value, which is negative 3. Two numbers that multiply by 2 and add up to negative 3 are negative 1 and negative 2. So the factored form is x minus 1 times x minus 2. Now we just need to set each factor equal to 0 to solve for x. Because if you have something multiplied by something equal to 0, that means each of those things are equal to 0. So you set each of them equal to 0. From here, x is equal to 1 and x minus 2 equal to 0. X will be equal to 2. So the x-intercepts are 1 and 0 and 2 and 0. On this function, y-intercept, and you set x equal to 0. So this will be 0 squared minus 5 times 0 plus 4 over 0 squared minus 4 times 0 minus 1. Again, all these are 0, so your answer will be 4 over negative 1, which is just negative 4. So y-intercept is 0 and negative 4. Now, what is my x-intercept? Just set the top equal to 0. X squared minus 5x plus 4 equal to 0. Now we need to factor this. Big X. On top goes 8 times 4. 8 times c, which is 4. On the bottom goes the b value, which is negative 5. The two numbers can be negative 1 and negative 4. If you multiply them, you get 4, and if you add them, you will get negative 5. So it's x minus 1 and x minus 4 equal to 0. Now you just need to set each of them equal to 0. X minus 1 equal to 0, then x is equal to 1. X minus 4 equal to 0, x is equal to 4. So your x-intercepts are 1 and 0 and 4 and 0. So this is today's lesson, we learned how to find x and y intercept and also horizontal and vertical asymptotes to graph a function. We will learn more on next lesson. Have a great day.